Hello, welcome to IEEE Sensors 2020 Track 9 Sensor Networks. My name is Edwin Khan, and I'm with my PhD student, Guoyi. Today, we're going to tell you about the RFID-based sensors in smart buildings. Next slide. The outline of the talk is, the talk will be for two parts. The first part, I'll tell you more on the visionary and the work, how the RFID can be used in smart buildings. I'll cover a lot of the general introductions instead of technical details. Okay. In the second part, we'll use one point, specifically the device-free occupant detections for the technical examples, how these all the technology, both on the hardware and the signal processing algorithm that's involved. Okay, first, I'm going to tell you about sensor network in smart buildings. The smart building should have the self-awareness of structure integrity. The second, it should have knowledge of occupants for the occupant center control. So the roles of the passive UHF RFID tags can be, first, can be embedded, the passive tags can be embedded inside load-bearing elements to detect slide, settlement, and vibration, normal or abnormal vibrations, so that through these sensing units, we can have understanding of the structure integrity. And we can have tags on occupants for ID and for locating the precision locating of the occupant, and we can retrieve the vital signs. Okay, and I'll give you examples for that. We can have tags on the ambient walls and furnishing for device-free occupant monitoring, not assuming that the occupant will wear a specific tag, but even with the device-free operations, that the ambient tag will provide some basic information about the occupant's location and posture. And we can have tags on furnishing and utility items for inventory, and this is apparent for the original use for the UHF RFID tags. Okay, I will talk less about it, but you can use your imagination. You have a lost key or something that has a tag, it can be located and can be ID'd. And then my student will take it over the second part of the device-free occupant detection and locating by the inverse method. Next slide. So in a smart building in the future, we imagine there will be many of the RFID-based sensors. Why RFID-based sensors instead of the other sensors? RFID has the unique advantage of it's passive, it's low cost, and maintenance-free. You don't have to worry about the battery life, you don't have to worry about recharging, you don't have to worry about recycling. Okay, there's no battery involved. It's having this unique advantage. And each ID, each tag have a unique item level ID for all tags. And this ID can be used for identification of the tag and also used for the signal isolation. So each tags, when they are communicating with the reader, is embedded in a digital isolation. And we can also understand that for all these sensors, it can be embedded in the most non-metal dielectrics. That means for say a load-bearing element, we can bury the tag inside the cement block, properly designed for sure, and then we can know the specific marker point of the motion of the slide and vibration of that marker point. And passive tag can be totally non-invasive to aesthetics because it can be behind wallpapers and fabrics, curtains and things, and still be able to interact with the readers. And the typical reading range for UHF RFID is 5 to 10 meters, sufficient in most of the room segments. On the right, I show different possibilities. There are paper-based tags. You can implement your tags on fabrics, or for prototype, you can do it on PCB. So the applications, including, as I mentioned, they can give you a structural integrity, but what you need is that you need to be able to monitor the motion to tenths of micron of precision. We can use it for occupant ID and locating. And this is related. You need to have sufficient number of readers in your building. You can monitor the occupant wellness. This will be wearables and for a lot of the wellness monitoring functions. And we can have device-free occupant detections, and then we can use ambient tags on the walls and furnishing to do that. And we can use it for item logistics, and this requirement is that it needs to be massively multiplex, can be massively multiplex, so that you can have thousands of the tags within the same building. Next slide. So for the examples of the structural integrity showing here for a load-bearing column, we can embed a passive tag inside and try to see its location or its vibration during either a truck is passing or something we induce that we study the motion of the barrier tag. And on the right is our experimental prototype. We have a tank that can contain either air, water, or sands, building materials. And we have a linear stage providing you with providing a micron level of motion that we can be monitored from the reader. Next slide. And this is a video showing that a tag in the tank I just showed you, how they move within water. Okay, and the tank now is filled with water. It's filled with sand. You cannot see it. Okay, so it's moving within water, and you can see it precisely track the entire motion. This antenna has been carried by the linear motor. Next slide. And this is the statistics from the last tracking. In air, we get a resolution of that today's ability. For sure, there's a lot of noise reduction and things we apply for the techniques that we can achieve these kind of precisions. In air, for the commercial RFID with the PCB tag I show you, in air we have 40 micron resolution. In sand, we have 17 micron resolution. In water, we have less than 5 micron resolution of the motion. Next slide. And also in 1 kilohertz sampling, you can track it in different, when the tag is moving in different velocity, it's still very accurate. You can see that you can go forward and backward in very high precision. And the sampling rate for now is 1 kilohertz, but for these RF systems, it's no problem to go above 100 kilohertz, okay? That makes a lot of the vibration sensing to be feasible. Next slide. And we can use it in other ways. Say you have 2 tags with a known distance to each other. Then we can back extract the permittivity of the media. Okay, what it shows here that we use 2 tags and we get, when the tank is filled with air, we get a permittivity is about 1. In sand, it's about 4.67, and the variation is a lot larger when we move that because sand is a grainy structures. That large variation is expected. In water, we get a permittivity of 78.7, which is very close to the literature values. And these can be used for detection of the structure material degradation. Say you have a metal structure inside a cement block, and it get rusted. Permittivity change, we can read from externally. Next slide. And let me switch to another possible use for these passive RFID tags. Is for occupant monitoring in assisted living. In shown here, there are tags of occupants, and we can get the locating and vital signs. We can have tags on chairs and the embed for covert and backup vital sign monitoring. Whenever the people sit or lying down on the bed, we can get the vital sign measurement directly. And we can have tags on ambient walls, and then we can use those tags to monitor the device-free occupants. Okay? And we can have tags on doors and windows for security, say to say whether the door or a window has been moved in a small motion. Okay? And we can have tags on essentials to ask questions like, where's the first aid? Okay, where they are located, whether they are in this room. Next slide. So I'm showing that say you have a heart is beating. We have a wearable as two sensors on top of the heart positions. Today we can trace this we call the Uyghur's diagram, the pressure transient of the heartbeat. And say for the antenna 1 is above the aorta, we can get the aortic vibration, map that into something we call the Hilbert-Huang transform, and then using the vibration frequency to map to the pressure. And then we can get the systolic and diastolic pressure. This can be applied to the pulmonary side as well, which is very difficult for any of the cuff-based measurements. So we place the sensors on top of the pulmonary artery that we can see how the get the systolic and diastolic blood pressure for the pulmonary circulation. Next slide. And this is a monitoring of the respiration. And you can see that we benchmark against the very uncomfortable chest belt, which is pretty tight, need to be very tight on your chest, or the face mask with the pneumotachometer. And we can almost achieve the same reading by placing a comfortable tag on the person to get all the breath waveforms, including the breath rate, respiratory volume, and from that we can derive the stress and the attention. Okay, next slide. And we can integrate them into furnitures. Here show chairs, and when we have the sensor implemented in chairs, so we can directly get the heartbeat, respiration, and femoral pulses on the leg. So for people, say you are waiting in this waiting room chair, or you are on the bed for sleep studies, the user don't even have to notice that the sensors are there, and the vital sign can be collected. Next slide. And the ambient text, which will be talk more further, our vision is that we put sufficient number of tags around the room that we can get the number, location, and posture of the occupants. In the middle, we show the 1 to 6 model, how in the conference room setup, how we can retract the model as they're standing or sitting and where they are. And this can be used to say replacing the battery power sensors on doors and windows. And also from the posture, you can detect whether people has been accidentally lying on the floor to trigger a full monitoring. Next slide. I'll give the time now to my students for the zooming in to the device-free occupant detection.
Okay. Thank you, dear audience. Hello, my name is Guoyi, and I'm a third-year PhD student from Cornell University. So in today's presentation, I will discuss the research work on using commercial RFID in combination with optimized inverse solution to resolve the problem of indoor device-free object sensing and detection. So why do we want indoor device object sensing? And why is it important? So here are some of the applications that indoor object sensing plays a role, where Professor Ken has already mentioned. It can help control heat, air conditioning, and ventilation systems and save energy. It can also be helpful for assisted living where the posture, gesture, positions, even health conditions of senior citizens is monitored and provides useful information for remote diagnosis. It also serves to provide extra security for smart home and smart building systems. Finally, it helps monitor and count occupants in public places or even assist in social distancing during COVID-19 pandemic. So in the past, lots of efforts have been in indoor object sensing. Optical methods include camera-based video and image processing and infrared camera. Piezoelectric sensors extract vibration or location. In particular, microwave techniques are widely researched in the past decade. On the one hand, different hardware systems are adopted, such as Wi-Fi and radio frequency identification, each with their respective advantages. And customized radio transceivers or software-defined radio have also been used to achieve indoor localization or imaging. On the other hand, signal processing algorithms are employed for different purposes. For example, learning-based fingerprinting were used for indoor localization by matching the received signal patterns with the training data. With sparsely constrained holes, compressive sensing algorithms have been employed to resolve the inverse problem. And conventional radar techniques like frequency modulated continuous wave radar, FMCW, Doppler radar, and receiver beamforming have also been transferred into indoor settings to resolve the object location. So how do we achieve this task? And our solution is to achieve indoor device-free object sensing through the combination of commercial off-the-shelf RFID systems and robust inverse solutions. Developed to a high maturity, its applications are limited and can be potentially extended to IoT. The real-time and large-scale inventory capability enables supply chain management. Large retailers, including Walmart and Zara, have used RFID systems in their logistics management. Asset inventory and tracking is made possible by high read rate, can be found in healthcare, airport baggage tracking, and so on. The unique tag ID and the ease of accessing the tag memory enables access control. And in recent years, more and more research are focused on how RFID can benefit the future IoT applications like smart building. This is because the state-of-the-art RFID platforms make it possible to extract the RF parameters like the received signal strength indicator, RSSI, and the phase. RFID has many advantages. It is low cost and extremely durable, which do not require maintenance. Sticker-like passive tags are easy to be deployed and do not introduce decoration or aesthetic issues. With established communication protocols, RFID is ready for commercialization. Therefore, we believe that RFID system is a candidate for future IoT platform with potential indoor device-free object sensing. However, there are some challenges imposed by implementing the RFID for indoor sensing tasks. First, signal-to-noise ratio is seriously degraded in a large room due to longer propagation channels and multipath reflections. Second, reader antenna gains cannot be indefinitely increased in pursuit of high SNR because of the trade-off between antenna gain and its 3 dB beam width. Because spatial diversity is a mathematical requirement for accurate indoor locating, reader antennas need to cover a large area of tags. With a smaller coverage area, spatial diversity is not achievable. Our contribution, however, in this work is to resolve these challenges in the practical scenario. So how do we solve this problem? Our hardware system consists of an active RFID reader and many passive RFID tags. Tags are deployed with spatial diversity. The way we determine diversity is through the use of case-based sampling shown in the definition and the 3D scatter plot in the slide. Locations of tags and reader antennas along with the carrier frequencies are used in the definition, and the plot shows much diversity in the spatial domain. Two types of reader antennas are used to study the antenna coverage and system SNR. The patch antenna has a radiation pattern in the shape of a beam pointing towards a specific direction. The dipole antenna, however, has an omnidirectional radiation pattern in the 2D plane and almost no gain in the third dimension. We compare the performance of both antennas in terms of SNR. The algorithm we use will be solutions to an inverse problem. Two solutions will be compared, where the proposed regularized truncated pseudo-inverse solution is superior than the conventional match filtering solution in terms of efficiency and accuracy. So first, let's take a look at the signal model and problem formulation. The downlink and uplink channels can be divided into two parts, one including the line of sight and the background multipath, and the other including only the target object reflection. At reader Rx, the receiver, both these two parts exist, but in order to extract the object location, only part 2 is needed. Therefore, we will need to first extract out part 2, which will be discussed in the next slide. Two assumptions are made. The first one is that the object is very small, and the other is that the object reflects the incoming signal into all directions. With the signal model and the assumptions in mind, we can formulate the problem by regarding the received signal as the summation of all the signals reflected from object in the captured volume. The problem can be discretized into matrix form. Before going to the inverse solutions, let's first take a look at how we perform the no occupant calibration to get the part 2 signal. The basic idea is to subtract the received signal collected when the room has no occupants away from the received signal when the occupant is present. That's the reason why the third equation is a subtraction. However, we need to make sure that the subtraction will result in only the signal with respect to object reflection and do not include other factors multiplied into the result, such as the reader antenna cable loss, antenna gain, tag circuitry loss, and other losses along the communication link. This part of it's denoted by the gamma in the third equation. And the first two equations are used for estimating gamma. is done by removing the line of sight propagation loss between the reader antenna and the tag. With known locations of tags and reader antennas, it is easy to get rid of the line of sight propagation loss by doing division. This whole process is called the no occupant calibration. The received signals after calibration is the vector D that we use here. Now we will start the discussion of two inverse solutions. The first one, which we term as the match filtering, is a simple solution by applying the Hermitian of the parameter matrix G onto the data vector D. If we perform the singular value decomposition, SVD, for matrix G, the solution can be written as a summation as shown in the slide. It is simple to implement, but very unstable against noise, because the small singular values on the denominators of the terms with a large I in the summation amplify the noise in the data vector D and destabilizes the solution. In addition, the number of observation points enabled by the tags, reader antennas, and carrier frequencies is typically orders of magnitude smaller than the number of voxels in the capture volume, especially for a large room. Therefore, the solution is highly underdetermined and thus prone to image ambiguity. The second inverse solution, which we propose in this paper, uses second-order regularization and truncation of the summation. The least square solution can be found for this new problem formulation with the regularization term. Again, we apply SVD for the matrix G, and the solution is also written as a summation, where the regularization parameter eta is lumped into the variable fi for each term of the summation, and is used as a penalty for the robustness against noise. We further apply truncation to this summation with parameter k, which means we only preserve the first k term of the summation and remove the term with small singular values and causing instability. Both regularization parameter and the truncation parameter are tunable. So the way to tune these two parameters are briefly shown in this slide. To determine regularization parameter eta, we need to find a balance between the accuracy of the solution and the robustness against noise. We can see from the two plots in the middle that as we increase the penalty on the second normal row, the residual term, d minus g row, increases, and the regularization term decreases. The very popular L-curve technique is adopted here, where the plot of the two terms is generated, and the turning point of the L-shaped curve is chosen to be the place where optimum regularization parameter happens. As for the truncation parameter, we look at the condition number of matrix G and ensure that it is not too large so that it is not robust against noise. We choose an empirical value of 5 to make sure that the solution is stable. So in our prototype for the reader, antenna, and tag locations, we compare 3 setups with different number of patch antennas and dipole antennas, shown in this slide. We can observe that the third setup, which consists of 4 dipole antennas, gives us the highest SNR, shown in the histogram plot below. Most of the channels have an RSSI larger than -60 dBm. This is because the dipole antenna deployed in the room provides an omnidirectional radiation to cover all the sidewall tags. Even when we increase the gain, the tags can still be covered. However, for the ceiling patch antennas, the beam becomes narrower as it points to the ground when the gain is increased, and the sidewall tags cannot be covered. So here we have a picture of the setup using the 4 dipole antennas. The tags are pasted on the cardboards to enclose an area of 365 centimeter by 365 centimeter. Dipole antennas are placed near the 4 room corners, and its space center is about the same height of most tags to ensure the optimal coverage. So we have applied the described inverse solution for object locating, and the single occupant results are shown here. We can observe that the truncated pseudo-inverse solution with regularization provides a higher locating accuracy as shown as the yellow markers. The ground truths are shown as red markers. The cumulative distribution function, the CDF, are plotted based on the 13 different locations in the room. And we can see from the distribution functions, the time, also the time spent calculating the inverse solutions are compared in the table. For the proposed truncated pseudo-inverse solution with regularization, it is superior than the match filtering method, both in terms of the locating accuracy and computational efficiency. Here are the selected results for 2 object cases. And we can see that the truncated pseudo-inverse solution is more robust against noise. It is more efficient and has more accurate locating. To summarize our presentation, RFID has many potential applications for smart building, including structural integrity examination and occupancy-centered control. RFID can also be used for vital sign monitoring, item-level inventory and locating, and device-free occupant detection to expand its present usage. In particular, we use truncated pseudo-inverse solution with regularization, which provide higher locating accuracy and lower computational costs than conventional methods to achieve device-free object detection. Dipole reader antennas enable a wider coverage of sidewall tags. So in conclusion, the RFID system is low cost and extremely durable. It is ready for commercialization and introduces minimal intrusion to indoor aesthetics. Therefore, we believe it is a candidate for future IoT platform. This is the end of our presentation, and we appreciate your attention. Thank you very much.